Swayam Prabha. Digital India. Educated India.
Welcome to the class. Till time we have considered that there can be an impulse turbine and then there is a necessity of compounding, and this necessity has led to two types of impulse turbines. One is the impulse turbine of pressure compounding type and other is impulse turbine of velocity compounding type. So we have seen that there is Ratu or Curtis staging of the impulse turbines. Now we will come out from the understanding of impulse turbines and we will move towards the reaction turbines. So today's discussion is majorly towards reaction turbine. So in case of reaction turbine, let us first understand what is the difference between reaction and impulse turbine. So in an impulse turbine we have nozzles. This is impulse turbine and this is reaction turbine. In case of impulse turbine, this figure is a demonstration from the perspective of the action or the working fundamentals for impulse and reaction turbine, and this is not exactly related with one-to-one related with the steam turbine, but in general we will have nozzle and we will have moving blades. So there will be enthalpy drop and pressure decrease in the nozzle, and then pressure doesn't change in the moving blades. Velocity will increase in the nozzle, then velocity will decrease in the moving blades. So this is what the fundamental in which impulse turbine works. The flow in the impulse turbine is such that the velocity is directly going to heat. Velocity vector is arranged such that there will be a stagnation point here, and which would lead to action or which would lead to an impulse to the moving blades, and then moving blades will rotate. However, in case of reaction turbine, we will have smooth flow into the moving blades. Here there is partial pressure drop, partially, or some pressure will drop in the nozzle and rest of the pressure will drop in the moving blades. So moving blades, unlike in case of impulse turbine, will face the pressure decrease. So this pressure decreasement in the moving blade will actually help to raise the relative velocity into the moving blades, and then we will have that relative velocity further consumed to the work generation or energy generation in the turbine. So there is absolute velocity which will be risen in the nozzle, and then that absolute velocity will decrease in the moving blades. So very first point what we should understand in case of moving blade, in case of impulse turbine, if we have impulse turbine and then we have reaction turbine. In case of impulse turbine we have pressure constant in moving blade. In case of reaction turbine, pressure changes in moving blades. So enthalpy is constant in moving blades, and then second, in case of reaction turbine, enthalpy actually is not constant and rather decrease in moving blades. As an outcome of this, relative velocity is constant in moving blades of impulse turbine, but relative velocity is not constant in moving blades of reaction turbine. So what is the maximum constraint? We have seen VR1 is equal to VR2 if there is no friction or friction factor is equal to 1. So maximum value of VR2 is equal to VR1, but here it would happen that VR2 is always greater than VR1. This is what the fourth point in case of impulse and reaction turbine difference. So we will move ahead and see how the impulse and reaction turbines would work. Very first point to be understood here is the degree of reaction. As we have stated here that there is enthalpy constant in the moving blades of impulse turbine, but enthalpy decreases. So there is an enthalpy drop in case of reaction turbine. So in case of reaction turbine, we have nozzle and moving blades. So there is delta H in the nozzle and then there is delta H in the moving blades. So there is total delta H in a stage. So this is what it will happen in case of a reaction turbine. So in view of this, there is a relation which states that there is degree of reaction. So degree of reaction R is defined as the enthalpy drop in moving blades divided by enthalpy drop in a stage. So there is total enthalpy drop in a stage, total absolute enthalpy drop in a stage, and how much percent of it is having dropped in the moving blades, that is degree of reaction. So degree of reaction will be delta H in moving blades divided by delta H in fixed blades plus delta H in moving blades, or delta H in moving blades divided by delta H in stage. So this is the degree of reaction. So what we mean here is if moving blades had zero enthalpy drop, so if moving blades had zero enthalpy drop, then it becomes degree of reaction 0. So it is a pure impulse turbine. If fixed blade has zero enthalpy drop, then degree of reaction is 1 and it becomes pure reaction turbine, or also called as Hero's reaction turbine or Hero's turbine. Now there is a very particular case which is of interest for us, mainly for solving the examples, where we will have equal enthalpy drop in moving blade and fixed blade. So they have enthalpy drop which is delta H by 2. So there is degree of reaction 0.5. It is called as 50% reaction turbine, or it is also called as Parsons turbine. So we have one parameter, one governing parameter, or one performance parameter, one parameter of the impulse turbine which should be known to us, and that is degree of reaction, which basically tells us the percentage enthalpy drop in the moving blade out of the total enthalpy drop in a stage. So now we will move for a particular case of 50% reaction turbine. Now in case of 50% reaction turbine, we will draw the velocity triangle. So the velocity triangle is as usual, we will have the blade and then there will be velocity which is appearing, which is coming into the blade, which is relative velocity, and then we have Vb which is blade velocity, and then we have V1. So as we had drawn the velocity triangles in the impulse turbine. So this is the V1 velocity at the entry, which is absolute velocity. This is VR1 which is the relative velocity at the inlet. As we had defined earlier, alpha 1 is the nozzle angle at the inlet, beta 1 is the blade angle at the inlet. Then since we have enthalpy drop in the moving blades, so relative velocity is bound to change due to change in enthalpy. So VR2 will have certain value. So we have VR2 and we have V2. So absolute velocity angle at the outlet is alpha 2 and relative velocity angle at the outlet is beta 2. So we will take it for granted few things for 50% reaction turbine, and those things would state that in case of 50% reaction turbine, we have V1 is equal to VR2. So V1 is equal to VR2. We have V2 is equal to VR1. So we have V2 is equal to VR1, and then it leads to alpha 1 is equal to beta 2 and beta 1 is equal to alpha 2. So this is a takeaway for a special case of 50% reaction turbine. Having said this, we can draw the velocity triangles for the 50% reaction turbine and write down the formulas as what we did in earlier case. Here delta VW is the change in velocity which is in tangential direction. We know here that in case of reaction turbine as well, or in case of impulse turbine, the tangential velocity VW1 is this and tangential velocity VW2 is this. So we have this complete distance as delta VW. So VW1 is equal to V1 cos alpha 1. So V1 cos alpha 1 is this distance. So this is V1 cos alpha 1, and VW2 is equal to V2 cos alpha 2. So this distance is V2 cos alpha 2. Practically we are writing it as delta VW is equal to V1 plus VW1 plus VW2. This is what we are writing. So here V2 cos alpha 2 can be expressed as VR2 cos beta 2. So this distance is VR2 cos beta 2 minus this distance is VB. So this distance is equal to VR2 cos beta 2 minus VB, and then we know this, which is equal to VW2. So delta VW1 becomes V1 cos alpha 1 plus VR2 cos beta 2 minus VB, but we know that VR2 is equal to VR1. So since VR2 is equal to V1, VR2 is equal to V1, so this VR2 will be replaced by V1. Similarly, we also know that beta 2 alpha 1 is equal to beta 2 and alpha 2 is equal to beta 1. We also know that alpha 1 is equal to beta 2. So this beta 2 will be replaced by alpha 1 and this will be replaced by V1. So we will have V1 cos alpha 1 as it is, and VR2 cos beta 2 will get replaced by V1 cos alpha 1 minus VB. So this is the formula for delta VW. Then this leads to the next step, which states that there is 2V1 cos alpha 1 minus VB, that is the delta VW. So we can use delta VW to find out what is the work done in a stage per kg of steam flow rate. Otherwise we have to multiply by steam flow rate. So this is delta VW into VB. So we have work done in a stage is equal to twice V1 cos alpha 1 minus VB into VB. So this is the work done by the 50% reaction turbine. Now let us find out what is the input energy to a stage. This is very important for us, since in case of impulse turbine we know that the kinetic energy at the exit of the nozzle is given as an input to the moving blades. So input kinetic energy was used to divide the work done to get the formula for diagram efficiency. So diagram efficiency in case of impulse turbine was work done divided by half m dot s into V1 square, and that m dot s into V1 square by 2 was the kinetic energy at the outlet of the nozzle or at the entry to the moving blades, but there whole enthalpy drop was taking place in the nozzle only. However, in the present case it is not true. In the reaction turbine we have enthalpy drop in the moving blades and in the nozzle or in the guide vanes also. So since in the stationary blades also we have enthalpy drop and we have enthalpy drop in the moving blades, we have to account the enthalpy drop in the moving blades. So this is the kinetic energy at the entry to the entry to the moving blades, and that is trivial since that was also available in the impulse turbine. But this is the kinetic energy which we got generated, we got changed, increase in kinetic energy on the moving blades at the expense of change in or decrease in enthalpy on the moving blades. So there are two kinetic energies which should be summed to get the total energy which was received by the moving blade to do the work. So we have this 1/2 V1 square plus VR2 square by 2 minus VR1 square by 2. Actually here we are assuming that entry kinetic energy to the nozzle is negligible in comparison with the exit kinetic energy. So 1/2 V1 square is the kinetic energy entry to the moving blades, and then we have 1/2 VR2 square minus VR1 is change in kinetic energy on the moving blades. So we have E in is equal to 1/2 V1 square, but VR2 is equal to V1. So we have again 1/2 V1 square and we have VR1 square half, which is minus. So these two will sum up, and then we have V1 square minus half VR1 square. But if we go back and see what is VR1, then this is VR1. So this is VR1, and then from the velocity triangle we can write down VR1 is equal to VR1 square is equal to V1 square plus VB square minus twice V1 VB cos alpha 1. So E in is equal to V1 square minus half into V1 square plus VB square minus twice V1 VB cos alpha 1. So we have this V1 square will go in, and so we will have half into V1 square minus VB square plus twice V1 VB cos alpha 1. Having known the input kinetic energy, we can now find out what is the diagram efficiency for 50% reaction turbine. So it is equal to blading efficiency or diagram efficiency is work done divided by E in, and we knew earlier that work done is twice V1 cos alpha 1 minus VB into VB divided by half V1 square minus VB square plus twice V1 VB cos alpha 1. We know that we are interested in finding out the optimum efficiency condition, and optimum efficiency condition is always corresponding to certain velocity ratio, and we had earlier also defined rho as a velocity ratio which is VB upon V1. So we want a ratio of rho which is VB upon V1. So we will take VB common from this bracket. So we will have 1 over here, and we will have V1 upon VB over here, and VB will come out, and then this VB is as it is. Similarly, we will take V1 square common from the denominator. So we have 1/2 V1 square. So 1 minus VB square upon V1 square plus 2 into VB upon V1, since 1 V1 will get cancelled into cos alpha 1. So this VB and this VB will constitute VB square, and this 2 will go into the numerator. So twice VB square upon V1 square into 2 into V1 upon VB cos alpha 1 minus 1 divided by 1 minus VB square upon V1 square plus 2 into VB V1 cos alpha 1. So this is the formula for diagram efficiency. So this formula will be placed by rho is equal to VB by V1. So we will have 2 into rho square plus into 2 rho cos alpha 1 minus 1, 2 upon rho cos alpha 1 minus 1 upon 1 minus rho square plus 2 rho cos alpha 1. We can put this rho square into the bracket, and then this leads to 2 into 2 rho cos alpha 1 minus rho square divided by 1 minus rho square plus 2 rho cos alpha 1. We can differentiate this formula with respect to rho and equate it to 0. This differentiation is same as what we use a product or division rule of differentiation. So this term is numerator divided by denominator. So denominator raised to minus 1 as it is. So we have first differentiation of numerator. So differentiation of numerator 2 is a constant, and then we are differentiating with respect to rho. So 2 cos alpha minus 2 rho minus, since it is a differentiation of denominator, so we will have raised to minus 2 into the differentiation of denominator. 1 is a constant, so it will have differentiation 0 minus twice rho plus 2 cos alpha 1 into 2 rho cos alpha 1 minus rho square. So we will equalize the denominator of two terms. So we will have 1 plus rho 1 minus rho square 2 rho cos alpha 1 into 2 cos alpha 1 minus 2 rho minus in the bracket minus 2 rho plus 2 cos alpha 1 into 2 rho cos alpha 1 minus rho square divided by 1 minus rho square plus 2 rho cos alpha 1 bracket square. Having said this, we will equate this with respect to 0. Denominator is not definitely 0, so we will divide it, multiply both the sides by this, so this will get cancelled, and then we will have a term which is 1 minus rho square plus 2 rho cos alpha 1 into 2, and then we will have 2 as a common, so it will be 4 into cos alpha minus rho minus 2 rho plus 2 cos alpha 1 into 2 cos alpha 1 minus rho square. So here as well we have 2, so here as well it will become 4. So this 4 and this 4 are there, and then further we have this term as cos alpha minus rho, and here also we have cos alpha minus rho. So these two terms and the 4 term will be common. So we have 4 cos alpha minus rho into 1 minus rho square plus 2 rho cos alpha 1 minus twice rho cos alpha 1 plus rho square, and this if we equate it to 0, we ultimately would get rho optimum, or rho is equal to cos alpha 1. So maximum efficiency of a reaction turbine will be obtained if we have rho or Vb is equal to V1 cos alpha 1. Then we can put it into the formula of diagram efficiency, and as per that formula we have 2 into 2 rho optimum cos alpha 1 minus rho optimum square divided by 1 minus rho optimum square plus 2 rho optimum cos alpha 1. We will replace rho optimum by cos alpha 1. So we will have 2 into the bracket 2 cos square alpha 1 minus cos square alpha 1 divided by 1 minus cos square alpha 1 plus 2 into cos square alpha 1. So that leads to 2 cos square alpha 1 divided by 1 plus cos square alpha 1. This is the maximum efficiency of a reaction turbine. Having said this, we have thus derived the formula for work done for a 50. We have first drawn the velocity triangle for 50% reaction turbine. Rather, we have drawn in general the diagram, velocity diagram for 50% reaction turbine. From that we found out the work done. From that we found out the first initially the input energy to the reaction turbine. Then we derived the expression for diagram efficiency, and then using that expression we found out what is the optimum condition for maximum diagram efficiency, and hence what is the maximum diagram efficiency. Having said this, we know now that rho optimum is equal to cos alpha 1 and Vb is equal to V1. So what is rho optimum? Rho optimum is Vb upon V1. So Vb upon V1 is equal to cos alpha 1. So Vb is equal to V1 cos alpha 1. But further, for 50% reaction turbine, we know that V1 is equal to VR2 and V2 is equal to VR1, and alpha 1 is equal to beta 2 and alpha 2 is equal to beta 1. So if we try to reconstitute the velocity triangle which was earlier like this, now this velocity triangle which was general for 50% reaction turbine becomes this in case of optimum efficiency or maximum efficiency case. Here this is V1, so this V1 and this VB will have a relation which is rho optimum, which is V1 cos alpha is equal to VB, and this is V2. V2 is having alpha 2 which is 90, which is equal to beta 1, and alpha 1 and beta 2 are equal. It leads again to VR2 and V1 to be equal and VR1 and V2 to be equal. Here we have VW2 to be 0, so delta VW1 is equal to V1 cos alpha 1 which is VB. So we have work done is equal to m dot s into delta VW into VB, which is VB square into m dot s. This is a particular case for 50% reaction turbine with maximum efficiency or optimum working of 50% reaction turbine. Now we will compare different turbines. So first we said that we will have pressure compounding. So if we have pressure compounding, so in case of pressure compounding, this was the HS diagram which we should be expecting. If we have 1, 2, 3 and 4 stages of pressure compounding, then first nozzle will have this enthalpy drop, and then this point corresponds to, this is first moving fixed blades, then this point corresponding to moving blade 1, then this line corresponds to fixed blade 2, this point corresponds to moving blade 2, this line corresponds to fixed blade 3, this point corresponds to moving blade 3, this line corresponds to fixed blade 4, and this point corresponds to moving blade 4. So this is the complete expansion in the turbine, which is a 4-stage turbine in case of pressure compounding. Now the same HS diagram will change like this in case of velocity compounding. Here suppose we are working for 2-stage velocity compounding turbine, but as we know, in case of velocity compounding we have only one nozzle and rest of the stationary blades are acting as guide vanes. So whole enthalpy drop is taking place in only one nozzle, and all the stages are sitting here at a point. If it is a 2-stage, then one point corresponds to all the 2 stages moving blades and corresponding stationary blades as well. If this is for 3-stage, then this point corresponds to all the 3-stage moving blades and also the stationary blades. In case of reaction turbine, we have 1-stage reaction turbine, we have 3 to 4 A dash as the enthalpy drop in the fixed blade, and then this is the enthalpy drop in the moving blade. So this diagram is for exclusively for single stage reaction turbine. This is for multiple stage or single stage velocity compounding, and this is for the multi-stage impulse turbine, which is pressure compounding. And then this diagram is same for the single stage impulse turbine, which is pressure compounding. Having said this, now we can compare the efficiency and rho formula. So as we see that in case of simple impulse turbine, we have derived rho optimum is cos alpha by 2 and corresponding efficiency is cos square alpha. In case of velocity or 2-stage Curtis turbine, optimum rho is cos alpha by 4, corresponding efficiency is cos square alpha, but it will be always lower than this due to the frictional loss. Then the reaction turbine has optimum alpha, optimum rho as cos alpha, or all these are 1 for us, and then this leads to cos square alpha 2 cos square alpha 1 divided by 1 plus cos square alpha 1 as the maximum efficiency for 50% reaction turbine. So here we discussed what do we mean by a reaction turbine and how to work out with the velocity triangle of a reaction turbine, how we can compare the performance of various reaction turbines based on the optimum condition. So, for that we evaluated what is the optimum condition for 50% reaction turbine. So, here we end the discussion for reaction turbine, and next time we will see the rest of the part of the steam power plant. Thank you.